to give you a background on earthquake engineering as well as seismology. Now, does any one of you know how to get the location of an earthquake or the about an earthquake source? Do you know how to get that from the perspective of seismology? Now, when you say earthquake, you have several terms. An earthquake occurs at a depth, not on the ground. So there's what you call as hypocenter, and this hypocenter is where the energy of the earthquake emanates. Okay, so right above the ground where the hypocenter is located, it is what you call as epicenter. And by the way, I'm using in Australia we usually spell instead of TER, you always use TRE, and it's a British spelling. So I'm using this because it's an autocorrect from my computer. Okay, so an earthquake happens here, and then right above the location of the hypocenter is your epicenter. Now, when an earthquake occurs, it emits waves all over everywhere from the source. And there are two types of waves that is emitted. One is called the P wave. Anon. Okay. Wala pa yung okay, shit. Now, basically, there are two types of waves that an earthquake, or when there's a seismic action, there are two types of waves emitted. One is the P wave. It's called like a primary wave or P wave, and the other one is S wave or the secondary wave. Now, these two waves are different from each other. It's different. Why? It's because the P wave travels very, very fast, and it has a high frequency but low amplitude. When I say travels fast, it's because it, like when you have a beam, you have this. You also have when you have a beam, for example, a longitudinal beam. When there is an impact on the beam, they are similar to this. There's a P wave and a S wave. Now it has a high frequency because it has a low amplitude, and the secondary wave is it travels slower, but it has a high amplitude but low frequency. So you can see here the two are exactly opposite. P wave fast relative to S wave, and P wave has high frequency, but the other one is low frequency and low amplitude, and the S wave is high, has a high amplitude. So when you talk about waves, usually there are terms that you should know. One is a cycle, And I'm sure that most of you knows what cycle. One cycle means, say, for in when there's say for example, we have some, there is an object here and it travels in a sinusoidal wave, and once it is back to its original position, that is what you call as one cycle. So there's also a term we call as period. So period means the time to complete one cycle, and it is, so say for example, if this cycle has a length, takes, say for example, 5 seconds to complete, that means one period is means one period is the period is 5 seconds. And there's also a term we call as frequency. It means the number of cycles per second. So it is the reciprocal of period. Okay, so usually in structural engineering, we are using this term period most of the time. But in other engineering, like for example, in, you know about this what you call that? I'm not, maybe in mechanical engineering, I think it's very common to use frequency, because sometimes a frequency is not measured by time. It is like, for example, a sound. Sound has its frequency, but you cannot measure it in seconds. So that's why you either have to use period or frequency. And in civil engineering, we usually use period. But other engineering, we have frequency as the main measurement of the wave. Okay. Now, um, I think you're familiar with this kind of ground motion. So this is the typical ground motion you can see from your seismogram. During an earthquake, is ground motion, and this kind of recording is shown. So what you might be thinking, why every time there's an earthquake, we always have this, we need this ground motion history. Okay, and by the way, in earthquake engineering, this is called as ground motion time history, because it's a history, because it doesn't mean that this is just a recording in one location. What happens is that, say, an object that is stationary at a single point in a place, and then it moves in this recorded in this the is its motion is this way. It's up and down, up and down, up and down, and up. Suddenly, in the long run, the motion is very amplitude is very small. That's why will lose you will lose the feeling that there's a motion, but actually there is something, there's still in motion that you cannot feel. So why we motion take a location of the earthquake, or where does the earthquake start? See here, In every ground motion history, you can tell where is the P waves, the S wave, and the surface wave. I'm not saying that where is the P wave, but you can tell the arrival of when is the time of arrival of P waves, the S waves, and the surface waves. What happens is that, um, as I said, P waves travel very fast. So the P waves always arrive earlier than the S wave. Now, as the S wave come into, mix with the P waves, that's why you can see an increase in the amplitude of the earthquake motion, because both at this time, both the S wave and the P waves are already in the mix. So you can see that there is an increase. But there's also what you call as surface waves. These surface waves is just a combination of waves that, due to the mixture of the P waves and S waves. But when the P waves and the S waves reach the ground, they become what you call as surface waves. And that is usually where the higher excitation happens. Okay, so now, how do seismologists utilize these P waves and the S waves? What's the importance of there in there? So I'm going to show you how to locate the location of an earthquake from the earthquake ground motion. So for example, you have two cars here. Say this is the S wave, this car, and this white car is the P wave. Now, suppose this, because P wave travels faster, so at a location A, obviously P wave will arrive early. Say, for example, it arrives at 9 in the morning, 9 a.m. exactly. Then a few minutes later, I shouldn't be calling this as wave, because the difference is just 10 minutes. This is impossible. So I'll just call this as car. Okay. Let's say this car, a P car arrives at 9, and then the S car arrived at 9:10 in the morning. Now, with this information, can we can tell, if we know the velocity of S and the velocity of P, and we know the difference time, the time difference of arrival, then we can tell the starting point of these two cars. Not exactly, not the exact location, but the distance from your location A. So that is the principle used to find or to locate the earthquake hypocenter. Say, for example, this one. Say, for example, T1 is the time for P wave to travel from hypocenter. So and we don't know, because what we know is that P arrived at 9 a.m. But this 9 a.m. doesn't tell us the time travel. It only tells us that at a point of time, 9 a.m. But we don't know how long it took for this P wave to arrive at 9 a.m. Okay, this Tito is also we say that Tito is the time for each wave to travel from hypocenter to location A. Now again, we know that it arrived at 9 a.m., 9:10 a.m., 10 minutes after P, but we don't know how long it took for each wave to come to location A. So we don't know this travel time T1 and travel time T2 are unknown. However, the speed of P wave is known. The speed of S wave is also known. So with this relationship, we also know the time difference of arrival. It's known because P wave arrive at 9. Wala nang suit. Okay. Aha. Okay. Come on. Okay. Now, so we know that the time difference is 10 minutes. Okay, so it's known. Now, from the principle of the basic piece of physics, you know, so that both distance is velocity times time. So since both is and wave travel the same distance, then we know that the distance traveled is for T1 P wave is V1, its velocity, times the time it took the wave to arrive at location A. And the same thing for S wave. It has a velocity and Tito. Now you see here, V1 is known, T1 is unknown, V2 is known, T2 is unknown. But we know that the time difference, that T2 is equal to T1 plus the time difference, which is 10 minutes. So we can substitute V2 times T2, which is this one. So what happened is that we can solve for T1. So V2 is known, V1 is known, dt, the time difference is known, and V1 is also known. So we can solve T1. And if we can solve T1, then we can solve the distance. Then the distance is actually V1 times T1. So from this, we will know that the distance from location A to the epicenter or epicenter is actually R. So what happened is that this is what you need to do. This is your location A, and we know that the earthquake epicenter is at a distance R, RA, from location A. So the earthquake origin must be within the circle. Okay, but we still don't know exactly where it is. Now, if there is another location, because earthquake waves travel all over the place. Okay, so if there is a seismogram or any an that can measure the ground motion, it can also do the same thing as here. So it can measure it can calculate the distance r and draw a circle. Okay, so what happens is that the earthquake, because there's only one earthquake source, that means, and that earthquake is actually within this circle, and also within this along this circle, I mean. So that means the earthquake can only be either here, this one, or here. But still, we don't know because there are two possibilities. So it needs a third location to detect the location of the earthquake. So if there is a third station that measures the ground motion, it can also do the same thing and construct a circle, and with these three locations, you will know that the earthquake epicenter is actually here. Now, until here, I want to ask guys.
Verify lang, Rabbit.
Huh?
Verify lang, confirm lang. So, the two type of waves, magdungan sila release from
Yeah.
the source.
Hmm. Yes.
The S wave and the P waves, magdungan sila release.
Oh, do it. Yeah.
Okay.
So that is why this ground motion recording is used to detect the earthquake location. Okay. Now you might be wondering. So what if um, by constructing three circles, it won't tell you a specific location because measurements can vary. Now, if that's the case, you have to adjust your R's until you can find the location of earthquake. That is why when there is an earthquake, there's always this first estimate of the location. And later on, later on, there will be correction of the location, correction of the magnitude. There are lots of corrections. Even yeah, the magnitude is also corrected most of the time. So you can see here that earthquake is really difficult to measure, and and even this ground motion. Yeah, this can also be very inaccurate sometimes because this ground motion is needs also to be corrected because um, the measurement, I mean, the seismogram has its own response. So you have to process this motion and filter the motion to see that to make it to adjust so that the motion is purely from the earthquake, not without being corrupted by other factors like ground, soil response and different type of responses. So ground motion recording is not really accurate, but you have a good idea. That is why I always maintain that do not treat earthquake numbers as like um, gravity. When you say 9.81, it should be 9.81. There's so many errors in earthquake measurements and numbers. There's so that's why I'm every time I talk about earthquakes, I don't express any confidence like it should be that number. there's always a risk of idea of the value. Okay? So now, uh, from again, what I observed in designing structures, because the code says that find the location of the nearest fault or source fault, and then we go to and we take this is the location, this is the distance from the fault, so the fault, the distance, and I will use this in my design. And again, I just want to make everyone to be aware that if you look at these earthquake occurrences, see here, these red circle, these are the earthquake epicenters. Now, there are also faults here, the lines, red lines. These are the faults designated by feeble. Now, can you tell me what do you observe of the faults and the earthquakes? Can anyone tell me your observation? Any,
Some,
any
yeah,
observation you can tell is fine. No, no wrong answer.
some of the dots did not actually did not fall within the line.
Exactly. Yeah. See here, if you plot if you plot the earthquakes, the earthquakes epicenters and the fault lines, you cannot see any earthquakes that exactly, I mean, um, along the fault line. Okay, so that's why when you design a structure and you look for a fault, seismic faults from faults, you don't you don't have to think that the earthquake should be from the fault, because earthquake can occur anywhere, and even uneven faults are not straight line. Faults can be slanted. It can be a very complicated geometry. So this is though, I mean, I just want to emphasize that we shouldn't treat the fault as the location of earthquake. Earthquake can be anywhere, but sometimes maybe you can see a trend that some faults are look. I mean, some earthquake occurrences can be near to the fault, but it's not exactly along the fault. And even here, see here, you can see there's a fault here, but you haven't seen any earthquake near to this fault. But look at here, there's no fault here, but you can see lots and lots of earthquakes here. So there's no trend. You can't see a correlation in this area. You can't see a correlation between the fault and the earthquakes. Maybe in Bohol, for example, you can see a correlation because there's a fault line here, and there are also earthquake occurrences in the surrounding areas, but not necessarily along the fault line. And okay, so I think I have just shown to you that you cannot predict an earthquake. So, okay, and next slide here. In this example here, there are lots and lots of earthquakes here, but maybe because there we have this see here, there's that Philippine range here, and it could be that the Philippine trends is not really vertical, but slanting. So it could be, that's why some of the earthquakes are in this location. So that's a possibility. So, but other than that, there are lots and lots of faults here, but you cannot see an earthquake here. So it's sitting all over the place in this example, in this map. Okay, so you might be asking, then how do we assess the risk of earthquake occurrence? We don't know exactly. We cannot depend on the fault mapping. So that's why there's a need for probabilistic seismic hazard analysis. Now, what is this probabilistic seismic hazard analysis? Okay, I'm done here. So now I will show you an example of probabilistic seismic analysis. Okay, here, so those who are using a license for CE, there's a probabilistic seismic hazard analysis. So say, for example, I will choose which one? Cebu City na lang kay doon sa amo. Okay, I'll check Cebu City. I will select Cebu City and then here. So now this is Cebu City. So if I choose Cagayan de Oro City, then PrimC will display Cagayan de Oro City. But if you want to be specific of the location, then you see here there is a cursor here. Then you have to move that cursor to the location which you are interested, like that, for example. And then click this PSHA, and then this one, it gives you magnitude, this magnitude, and this hypocenter. Now, what does this magnitude 6.1 here and this hypocenter? It doesn't mean that you will experience exactly 6.1 and exactly 18 kilometers hypocenter. What it means is that for a return period of 475, what this means is that every 475 years, this earthquake of magnitude 6.1 with a hypocenter of 18.97 will occur. What I mean is that this location indicated by this cursor will expect to have a magnitude of 6.1 and 18 kilometers with a return period of 475 years. That's actually, so it doesn't also mean that it's only once, well, exactly 475 years. It means that on average, this is the return period. So it can be that within 475 years, you could have two of these, but in the next 475 years, there's none. So basically, it's not just the expected, from a point of statistics, it's the expected magnitude and hypocenter. And this magnitude and hypocenter is used to simulate the earthquake ground motion. Okay. Now, there's also a very interesting thing here that I want to show. For example, if I will increase the distance to 30, for example, and then do the simulation, what you will see is that the acceleration decrease, but the duration increase. Say, for example, I will change 50. So, and then the more the distance, the more you can see a reduction of the what you can see as the peak ground acceleration, but you can see an increase in duration. If I see, okay, for example, see here, I mean, if you increase the distance, the duration increase, but the peak motion decrease. So basically, that is the earthquake ground motion. Okay, so what else? Now, actually, there is also another criteria for conducting a probabilistic seismic hazard. It's called reliability. Now, it's not really used within the structural design community because structural engineering is basically deterministic. They want a specific number. They don't want probabilities. But in probabilistic analysis of seismic hazard, you can also use a criteria for reliability. Say, for example, if you have a building with a design years of 100 years of design life, and you have a reliability of 95, meaning meaning that you only allow 5% of error, and then you can do a seismic analysis, seismic hazard, and this is what you get. Now, if, say, for example, you increase your design life to 200 years, then you will expect that because it has a longer lifespan, you will expect to have a bigger, greater magnitude. Let's see, 6.4. Now, see, it's 6.5. So this is usually adapted in and see what you call it as a reliability engineering, wherein we specify the design life and the reliability. Now, if you want to increase, if you want to have almost perfect, so you have to increase your reliability, and then do the analysis, and you see the magnitude increased to 6.7, and the hypocenter becomes shorter. But I should have explained you more on this, but I have not prepared the slide. Maybe next time I can give a better explanation on what is this reliability and design life and this kind of thing. But so what I'm just showing is that in frame CE you can do a lot. You can do lots and lots of reliability analysis of earthquake motion. But the sad thing of this is that it's not really popular in structural engineering, and no one is really. I mean, I'm not sure if any one of you has encountered somebody using a reliability engineering index for design of structures. But when I was in Japan, we did some reliability analysis of structures, and we use this kind of analysis. Okay, so what in Philippines and in the standard, what is being used is just the return period. I know that there is a return period of, I think, 455 years, or there's like 1,000 years, something like that. So with frame CE, if you want to use the standard, you can do this. use the criteria for return period, go to seismic hazard, and then go to menu, and then print the report. This thing. Okay, and then okay, see here. This is the report print out using frame CE. See here, I think there is this is for 475 years. So if you the expected peak ground acceleration is 529. I think this, I'm not sure what is this. Maybe this is 2,500. So frame CE will plot the return period against the peak ground acceleration, and you can do an interpolation to get the expected peak ground acceleration. So basically, that's the importance of seismic hazard analysis. Now, if we go to design of structures, loads. Okay. Now, see here. You can also apply the seismic hazard analysis with regards to determining distance to the known seismic source. Now, I know that most of you are using fault finders from Peebles, so you get the distance from the fault, and then whatever you've the distance calculated, you just use that to designate your distance to known source. But actually, although this is code, but I don't like the idea of saying distance to known source, because nobody knows where's the source. Maybe you can say you know the fault, but as I've shown you in the slides, that earthquake can occur anywhere. So this is just to comply with the code requirement, but I don't really trust this kind of designating or idea of telling someone that you know the source. So that's why if I am the structural engineer, I always use in conjunction with this code requirement, I also do another checking using the seismic hazard analysis. But seismic hazard analysis is not really required by code, but it doesn't hurt if you do a checking. And sometimes also you need to have sometimes you also need to have the response spectra, and you can use this response spectra. You can export this by this sed command, and then you can export the response spectra here. So you can also use synthetic ground motion, or you can get the synthetic ground motion from seismic hazard analysis. And you might be asking, where did I get all this data? Is this magic like that? But it's not. When I was studying in Japan, our laboratory collected data from the Philippines all over Japan, and then we did a lot of analysis for different ground motions, and we had this statistical analysis for all the ground motion. And the laboratory where I was studying was able to develop a code that we use to simulate the ground motion. So actually, I learned this from the university where I was studying. Okay, and then now I'm not sure. I think I I have to stop here. And if you have questions, you're free to ask. Any questions, guy? Guys?
Ready,
Ah,
ready. Bean, it's bean.
saga,
Hello.
saga. Okay, okay. Sabihin?
In the ano ba, in the frame CE, the
Hmm.
seismic load computation, do we need to change the period, the
Um,
time?
I I don't think. I mean, because this is based on the code. I'll check. Analysis.
In the seismic calculation?
This one.
Yeah.
Um,
NNT,
I
yeah.
don't think. I know. I know. I should have hid. I should have hidden this. I know you don't have to. This is not requirement. Actually, this is not used. I should have. Say, don't.
So it's not part of the calculation. And the T that we compute will be uh, inputted in the.
No. I
Okay.
think it's yeah. That's a good pick up, Bing, because I thought I deleted this one, but it's still there. Hmm. Is that all, Bing?
Also, does it include the for the past 10 years or the past years? Sense like is in terms of the updating of the map, does it include
Yeah.
the past 10 years or the past 20 years country?
Think I the last time I mean that okay in the seismic hazard I used developed it used the earthquake occurrences from 1900 until 2006 when I arrived in Australia. So basically, it's like a 100-year record of earthquakes, not just 10 years or 20 years.
Yeah. So will there be an updating back, Rabi?
Yeah, if
Considering that there is large earthquakes said occurring in the Philippines for the past 10 years or the past 20 years.
yeah, I think that's a good idea. We can update that. I can update that. But if you're just talking about the last 10 years, yeah, but I mean because the record was for the last 100 years, so changes because it already 100-year record of earthquake. Yeah, but of course there will be changes, but it could be minimal. Any question? Now, actually, I mean, I will go back to my slide here. Now, even without seismogram, actually, when there is an earthquake, and if you can approximate or you can have a good estimate of the location of earthquake without using any instrument. Say, for example, there is an earthquake and you are located here, and then if once you feel the earthquake, you can call one of your friends somewhere and ask them, oh, what time was the earthquake started there? And then you also call someone from another place and ask this somebody in location C what time was the earthquake motion started in location C. And from that, you can estimate the location of earthquake by just calling your friends. That's very, I mean, fun about earthquake earthquake location investigation or earthquake location.
Also, Rabi, can we estimate the succeeding ground motion after the rupture?
Well, there are, I mean, if you have, if no, I mean, for a normal person, for a common person, it's hard because um, there are many things to consider. So there's always it needs an expert for in seismology or ground motion simulation to um, to do that.
Also, Rabi, can you discuss to us regarding the height of the building in terms of the the motion of the building with respect to the magnitude of the source of the earthquake?
Ah, it's
Yeah, because
not
I saw the shorter the building, the higher is the horizontal displacement of the building. The smaller the building, equal.
obviously, yeah. There are two things to consider in earthquakes. One is that you have to consider the dominant frequency of your ground motion. See here. If you have a ground motion like this, you can decompose this motion into frequency domain. When I say frequency domain, you can decompose the earthquake ground motion into different frequencies like this, and then you can see which frequency dominates the motion. And then you also have to consider the frequency of your structure, the dominant frequency. Say, for example, um, just structure has its dominant frequency, and a ground motion also has a dominant frequency. So if the frequency of your ground motion is very close to the frequency of the structure, and that is where you can have what you call that as a resonance frequency, and it will have a huge impact to your horizontal displacement. But again, that's not an easy thing to do because there are so many things to consider. So that me as an earthquake engineer, I cannot say that um, it's easy. It needs a lot of assumptions. So the only thing you need to do is just to do some frequency analysis of your structure, and then consider what a motion frequency is dangerous to your structure. But other than that, it's difficult. That's why everything when you don't know anything, when you don't know, you have to do the risk analysis. It's not. I heard some people are saying, oh, we can estimate this we can estimate the magnitude, and with magnitude we can estimate the motion. I will say that that's not true, because even when you have even when there are earthquakes of the same magnitude, you don't expect that those earthquakes to have the same maximum peak ground acceleration. You don't expect those earthquakes to have the same duration. You don't expect those two earthquakes to have the same response spectra, because response spectra is also dependent on the structure. So it's that's why earthquake engineering is very complicated, and for me the best thing to do is just to do the risk analysis. But because as an engineer, we need to have an assurance. Like we need to assume something. We need to be um, assured that what number to use. That's why the code nominates a number. But I know that the code always have a disclaimer that they cannot guarantee that your structure will be still undamaged after earthquake, even if you're using the code. There's always a disclaimer to that, because nobody knows exactly what happens during an earthquake. So I think that the more you study earthquake engineering, the more you realize that you don't know earthquakes. So I'm not saying you don't know earthquakes, but it's hard to make assurance. The best way is to